Welcome back to eCoreAcademy, everyone. My name is Anita Raj, and I am one of the co-founders here along with my younger brother, AJ Raj. As you can see, I'm also the teacher of Biology 1 here at eCoreAcademy, and today we're going to be covering a new lesson which is called Properties of Water. Since this is part 3, for those of you who haven't seen my other 2 parts, there are 2 other parts that exist. The part 2 is going to be linked in the description box, but to find all 3 parts organized sequentially, you can go to our YouTube channel and you can find the whole Biology 1 playlist. So not only will you have access to Properties of Water, the 3 videos, you'll have access to all the Biology 1 videos I've done so far. So in this specific video, we're going to be kind of concluding our videos in which we solely focus on water so that we can move on to pH and then we'll get into macromolecules. So in this video, we're going to be talking about some of the 3 more properties of water that I want to cover with all of you because I do think these properties of water are going to show up in your classroom. Some of the, for example, the high specific heat that you see listed here, it's going to be more relevant than high heat of vaporization just because at the Biology 1 level, we study more about things that are a bit easier to grasp. So high specific heat is a bit easier to grasp than high heat of vaporization, but that doesn't mean that it doesn't appear in the textbook, and that doesn't mean it might not appear either on a test in your class, or if you decide to take AP biology, it's not a guarantee that it won't appear in those places. So it's best that you do learn about it now. So the reason I have this picture, I thought it was a pretty cool picture. It's of a beaker of water getting heated on a stove. It's because 2 of the properties of water that we're going to focus on today are going to be heat-related properties. So I just thought that was kind of cool. So the first property we're going to focus on is the high heat of vaporization, then high specific heat, also known as specific heat capacity. That's why I put it in parentheses. And lastly, we'll talk about how water is a universal solvent. So I'll get into what all of those terms mean in this video. But before I begin, I'd really appreciate it if you all could hit the like button, hit the subscribe button, hit the post notification bell, drop a comment down below, and share using our socials. Your support means a lot to us, so please show any appreciation you have by doing those things. So let's get right into it. Before I talk about any of these heat-related properties, I think it's important to review the structure of water. We're mainly going to focus on hydrogen bonds, which is what I covered in the last video, because in the first video, we talked about just a plain water molecule. So we talked more about the internal structure of one water molecule. And then last video, we talked more about external. So we talked about multiple water molecules associating with one another. So let's review hydrogen bonds. So as you all know, water has polar covalent bonds internally and hydrogen bonds externally. Water is a molecule that consists of 1 oxygen atom and 2 hydrogen atoms. The bonds between those atoms are polar covalent bonds, so those are the internal bonds found within a molecule. But then between different water molecules, you're going to find hydrogen bonds. You're going to find these hydrogen bonds between the hydrogen atom of one water molecule and the oxygen atom of another water molecule. Those hydrogen bonds are what hold water molecules together in, for example, a liquid, a gas, or even a solid. Those states of matter include many water molecules together. For example, when you fill a cup of water, you don't just have one water molecule. You have thousands and thousands of water molecules all bonded together by hydrogen bonds. So let's focus more on the hydrogen bonds now. So hydrogen bonds form when the negative parts of a molecule attract to the positive parts of another molecule. So as we talked about, water is a polar covalent molecule because the bonds within the molecule are polar covalent. Oxygen, if we look at the periodic table, has 6 electrons in its valence shell. And like the other atoms on the periodic table, it's trying to get 8 electrons in its valence shell to achieve the same configuration as noble gases, because the noble gases are stable and all atoms are working towards that stability. So oxygen is searching for 2 more electrons. Hydrogen is a special case because it doesn't need 8 electrons to fill its outer shell. It just needs 2. It only has 1, however, so it's looking for 1 more electron. So what happens is the oxygen atom is going to bond to 2 hydrogen atoms. The hydrogen atoms are going to share one electron each, and then the oxygen atom is going to share 2 of its electrons. So at the end of the day, I'll show you a picture as well. The hydrogens are going to be sharing 2 electrons with the with the oxygen, and then the oxygen is going to be sharing those electrons, but it's also going to keep 4 electrons to itself. So the hydrogens are sharing both of their 2 electrons. Oxygen is sharing 4 of its total electrons, and then it's keeping 4 to itself. So because the electrons are being shared, it's a covalent bond. Remember, ionic bonds are the other type of bonds we talked about. Those are the bonds where electrons are completely given away by one molecule and given away by one atom and taken by another atom. For example, sodium chloride, which is table salt, NaCl, sodium gives up its 1 valence electron to chlorine, which has 7 valence electrons. It's desperately searching for that last electron. So while these 2 atoms, the sodium and the chlorine, don't share that last electron, instead, the sodium will entirely give up that atom to the chlorine. That's ionic. Covalent is where it's being shared. So the oxygen is sharing electrons with the hydrogens, and it's polar because one part of the molecule, like we see here, is partially negative. That's where you see that little S sign that I've showed you on previous diagrams, and then you see the minus sign. And then one part of the molecule is going to be partially positive. That's where you see that S sign with a plus sign. So because the oxygen is sharing 4 of its electrons, but it's hogging 4 of its electrons to itself, it's going to have a more partial negative charge because it has more electrons. Remember, electrons are negatively charged subatomic particles. Meanwhile, compared to the oxygen atom, the hydrogens are going to be partially positive because they're both sharing their 2 electrons with oxygen. They're not hogging any electrons to themselves. So it's literally just, you're going to see if you see a diagram, you'll see the 2 electrons of hydrogen kind of pulled towards the side where it's bonded to the oxygen, and the proton is left all by itself, kind of. So that part of the entire water molecule where the hydrogens are, that's partially positive part of the molecule, and that's what makes it polar. Polar means both ends of the molecule have different charges. But that's also what helps with hydrogen bonding between different water molecules. Because one water molecule has a negatively charged oxygen and then 2 positively charged hydrogens, this water molecule is going to have a hydrogen bond with another water molecule. And I think I can go to the next slide. Yeah. And to the next bullet. So I might as well just show you the diagram now. So here you have your oxygen, and up here where my laser is where those 4 electrons that the oxygen is hogging are. These are your hydrogens. They're each sharing 2 electrons with this oxygen. That's what these filled in lines, it's a ball and stick model, so you can think of these like the sticks. These represent the 2 electrons that are being shared per hydrogen. And then over here, the hydrogen is not hogging any of its own electrons, so this part of the water molecule is going to have a partial positive charge. This part of the water molecule is going to have a partial negative charge. That's why we have covalent bond here. But the hydrogen bonds are going to occur between different water molecules. So they're not going to occur within a water molecule. Within a water molecule, you find covalent bonds. Outside, you find hydrogen bonds. Because these hydrogens are partially positive, because the oxygen is hogging most of the electrons, they're going to be attracted to the partially negative oxygen of another water molecule, because remember, opposite charges attract. So negative charges will attract positive charges. Meanwhile, positive charges will repel positive charges. Negative charges will repel negative charges. So that's why these hydrogens have formed hydrogen bonds with the oxygen of this water molecule down here. That's why they're also shown as dotted lines, because I want you all to take into note that hydrogen bonds are not really bonds, they're interactions. They're easily broken as water molecules just glide past one another, especially in a liquid or a gas when they just bump past each other and go in opposite ways. They're temporary, but they have very important, characteristics that supply to the properties of water. There are 2 types of properties I want to just recall to your memory. Cohesion, we talked about this in the last video. So cohesion is going to be hydrogen bonds between water molecules. So cohesion is pretty much attraction between 2 similar molecules. So it's going to be attraction between two water molecules. Water molecules are similar, they're exactly the same. They're both water molecules. And they're attracted to each other because, like we said, the partial positive hydrogen of one water molecule is going to be attracted to the partially negative part of another water molecule. The flip side, we have adhesion. So adhesion is going to be the attraction between two dissimilar molecules. So for example, I have here, it's like the attraction between a water molecule or a glass or the side of a glass test tube. We talked about in the last video called a meniscus. So it's like a curve you'll see at the top of the test tube. It's because the water molecules are attracted to the glass of the test tube. So almost like the glass test tube is going to pull on the water molecule. So that's why you see a curve. Specifically the water molecules on the very edge of the surface that are directly touching the glass, they're going to form hydrogen bonds with the glass and be pulled upward in that meniscus curve. And also along xylem lining. If you don't remember what xylem are, they're like plant veins that transport water from the roots up against gravity into the stem and into the leaves. So because you're working against gravity, you're going to have another force that helps propel the water upwards. And that is going to be adhesion. So water molecules are attracted to the actual lining of the inner lining of the plant vein. So the inner lining of the xylem. That's why I wrote xylem lining. So they're attracted to that, and because they're attracted, they're kind of going to climb their way up until they reach the leaves, whatever location they need to reach. So these water molecules are going to be forming hydrogen bonds with other surfaces such as the glass or the xylem lining. So that's your review of hydrogen bonds. Let's talk about the first property, which is high heat of vaporization. Water specifically has every molecule pretty much has a heat of vaporization, which I'll talk about. But water specifically is special because its heat of vaporization is high. Don't think that every molecule has a high heat of vaporization. It's just water specifically has a high heat of vaporization. I'm not saying other molecules don't have a high heat of vaporization, but we're going to be focusing on water, and it's special because its heat of vaporization is high. So before we even get into that, let's talk about vaporization. So vapor. So you've all probably heard of water vapor. So water vapor is pretty much when you change from a liquid to a gas form. However, you haven't necessarily gone up all the way to boiling point. So for example, water's boiling point is 212 degrees Celsius. Sorry, Fahrenheit, 212 degrees Fahrenheit, and I think 100 degrees Celsius. So water vapors pretty much form when you're kind of close to that. So I think like 200 and you could be around 210 degrees, like tottering around there, but you're not necessarily at the optimal boiling point, but you're still able to get water to change from a liquid into a gas. So there's not a, so it's pretty much defined as vapors form when there's not a significant change in temperature, but you're still able to get a liquid to go to a gas. So the temperature is constant, but it's high enough that you can change that liquid into a gas. However, if you simply just increase the pressure, you'll be able to easily turn that gas back into a liquid. So that's what vapor is, and vaporization is the process by which you turn a liquid into a gas. So it's when an element or a compound such as a molecule such as water is evaporated. So evaporation is when you're just making the surface of a liquid turn into a gas. So it's just the surface, or if it's boiled, you might have seen your parents, or maybe you, boiling water on the stove, and you see all of that water, not just the surface. You see all of that water turn into gas. So that is called boiling. That's when you actually boil the whole thing. That's why I wrote bulk. So the whole quantity of water is just being evaporated. Is being evaporated, but because the whole thing is getting evaporated, it's called boiling, because we change it from a liquid to a gaseous state, like we were talking about. Specifically, heat of vaporization is the amount of energy needed to convert a unit mass of a liquid at its boiling point into vapor without an increase in temperature. So let's say you have a liquid, you put water on the stove, liquid, you have a unit mass of a liquid. So let's say you only put like 1 gram of water on the stove in a tiny pan. And then you turn the stove up to 212 degrees Fahrenheit, which is the optimal boiling point for water. And then heat of vaporization is specific. So we all know that if we turn the stove up to 212 degrees Fahrenheit, that liquid water is eventually going to be turned into a gas, because when we add that heat, the you get your water molecules to kind of brush up against each other to move really quickly, and then they suddenly start breaking apart. And as you all know, when we make something colder, the atoms, molecules are going to come closer together. They're going to contract. That's why when we make something colder, the molecules come together and form a solid. However, when we add a lot of heat, they're going to pull apart and they're going to expand, and that's what happens with water. So when you add heat, when you turn the stove up to 212 degrees Fahrenheit, you're actually going to turn the liquid into a gas. So heat of vaporization is specifically talking about the amount of energy you're going to need to turn that liquid into a gas without having to change the temperature. So the temperature is constant. It's going to be at 212 degrees Fahrenheit. But how much energy am I going to have to add to change that liquid into a gas, into a vapor? So that's what heat of vaporization is. So you can think of heat of vaporization as how much heat is going to be needed to change a liquid to a gas. So that's pretty much it, just dumbed down. Um, and water has the highest known heat of vaporization. That's why I call this high heat of vaporization. It's at 540 calories per gram at 100 degrees Celsius. So 100 degrees Celsius is the boiling point. You obviously don't need to memorize this, but for all of you who like numbers, who like to quantify things, I thought this would be just cool to include. And I want you all to just think for a second. Why does water have a high heat of vaporization? Why does it take so much energy to convert water from a liquid to a gas? You have to go all the way up to 212 degrees Fahrenheit, and that is not a low number. Well, if you all think of it this way, remember how we talked about in the last video how hydrogen bonds are super special because they're able to regulate temperature? They're able to regulate temperature because when you heat up water and you want to turn it into a gas, the hydrogen bonds between the water molecules are going to absorb a lot of heat. That's just their characteristic. Hydrogen bonds tend to absorb a lot of heat, especially in water molecules. So as you raise the temperature, instead of the water as a whole, instead of all the water molecules getting agitated and kind of spreading apart and expanding as you would expect them to do, the hydrogen bonds between them actually will absorb all of that heat, so the water itself doesn't get hot very quickly, if that makes sense. It's almost like you're attacking the water with heat, but the hydrogen bonds are going to absorb all of that heat so that the water itself does not increase temperature very rapidly. So the hydrogen bonds are going to take the brunt of the heat. So that's why you got to heat up water really high, all the way up to 212 degrees Fahrenheit or 100 degrees Celsius, because that is when you kind of overwhelm the hydrogen bonds and they can't absorb any more heat. So then the water molecules are finally compromised. So then they will turn from a liquid into a gas because you just added enough heat to do that. Um, and it also is on the flip side as well. So if you're actually cooling a liquid into a solid, so you're cooling water, like liquid water, into ice, what happens is it's also resistant to temperature change. So when you're trying to make it colder, what happens is the hydrogen bonds will realize that the environment is getting colder. So they have all of that stored heat energy. Remember how we said that hydrogen bonds tend to absorb and store that heat energy? They'll actually release that heat energy when they realize the environment is getting colder and colder, and that will make the water molecules stay a bit hotter, so it'll make them resistant to becoming colder. So that's how hydrogen bonds help with heat of vaporization. And again, this is all due to the hydrogen bonds, so they're really special. And like we said, helps with temperature regulation, but I'd like to talk about how it does it in ecosystems. So remember how we talked about how organisms are we're really fragile in a way, because we do not do well when it comes to fluctuating temperatures. So imagine you're living somewhere and the temperature during the day it's all the way up to like over 100 degrees, but during the night it's like sub 30 degrees. You're not going to do well in that. Just from a biological standpoint, an organism is not going to have a lot of fitness. It's just not going to thrive and do well in an ecosystem like that, compared to an ecosystem where the temperature is more constant, and if the temperature does change, it's gradual so that the organism can adapt to that temperature. So that's where water comes into play. It helps with that temperature regulation in ecosystems. Um, I'll give you some examples exactly how so. So let's talk about the water cycle. So you all know what the water cycle is. It's pretty much just how water is recycled and how it flows through our ecosystem, how it pretty much just goes from streams to lakes, streams to rivers to lakes, or it empties into oceans, and the heat energy from the sun, because of heat of vaporization, is going to turn that it's going to the sun has to heat the water quite a bit until the water on the surface finally evaporates, and then it becomes a water vapor. Then it'll condense into clouds, and then when it's condensed enough, it'll fall back down to the earth as precipitation, and the whole cycle starts again. So with the water cycle, let's focus specifically on when it rains. So heat is released. So how exactly does that work? So think about it this way. When that water is evaporated from, let's say, the ocean surface or a lake surface, it's being evaporated, remember, because only the surface is being turned from a liquid to a gas. So when the surface of a body of water is evaporated, water molecules are going to go up into the sky, and then they're going to condense into clouds because it's a bit colder as the higher and higher you go up into the atmosphere. So they're going to condense a bit into clouds, and then finally they're going to turn back. The temperature is going to drop so much that they turn back into a liquid. But remember, as they turn back into a liquid and it rains, usually when it rains, we feel a bit cold. We feel like we shiver a bit, right? Because we're getting hit by water that came all the way up from high in the sky, where it's much colder up there in the atmosphere. So we're getting hit. We shiver when we get soaked by rain. We're like shivering. However, water actually helps us from freezing, because what it does is when you change from a gas to a liquid, water molecules are being cooled down. Remember, they're up there in the sky. They're being cooled down so that they can change back, so that they can be so that they can contract and kind of go from gas, which is really where the water molecules are kind of just zipping all over the place. They can kind of contract back into a droplet and fall. So what happens? The hydrogen bonds kind of realize, I'm personifying them. They're not actually people, but but kind of realize that the environment's getting colder, and what they'll do is they'll actually release heat. So even though you're cooling the water molecule down to turn it from water vapor into a droplet, because you're cooling it down, the hydrogen bonds are going to release heat. So it actually warms up the ecosystem, even if it's raining, even if it feels a bit chilly. Hydrogen bonds release heat, so we don't all freeze just because of rain. And then when water evaporates from the surface of a body of water, the ecosystem will cool. So remember, when water evaporates, the molecules are getting pulled farther apart. You're adding heat. That's how it's turned. Remember, heat of vaporization. You're adding heat to the water in order to change it into water vapor. However, when you add heat, remember that if you add heat, like, let's say it's a really hot day and it's an ecosystem by a lake, and a lot of water is evaporating, and there's a lot of energy from the sun. The whole ecosystem is going to heat up because of that direct sunlight. However, the water that's evaporating is going to be changing from a liquid to a gas. But remember, when there's a lot of heat, water tends to absorb that heat. That's why it has such a high heat of vaporization. It takes so much heat to turn water from a liquid to a gas, because the hydrogen bonds just keep on absorbing heat. And what the hydrogen bonds will do, they'll absorb heat so that the rest of the ecosystem doesn't get so overwhelmingly hot. So the ecosystem is going to cool down a bit. So that's how water helps when it comes to high heat of vaporization. So that's all I have for you today. I hope you enjoyed this video. Last one on water molecules. I know we're going to miss them, but we're ready to move on. If you enjoyed this video, please hit the like button, subscribe button, post notification bell, drop a comment down below, and share it using our social media shown here. You can also email us at eCoreAcademy@gmail.com if you have any questions or anything at all, honestly. And lastly, please check out our website when you can for all the additional resources. Have a great day, and see you in my next biology video.